Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome, everybody. I'd like to introduce Jonathan Smith, who is a professor at the University of Pennsylvania, and actually just coming back from 3 years of government service at DARPA. He's back at UPenn and is going to talk to us about SwitchWare, which is a project that he's been working on for a number of years. So, Jonathan.
Thanks, Jim. So I'm no longer working on it, although I am trying to extract ideas from it. That's probably a better way to state it, because the project ended in the early 2000s. So what's SwitchWare about? Well, the basic idea was to think about dealing with being able to change the internet. And changing the internet from the perspective of somebody who writes code means being able to code, so that you can take your ideas and create artifacts and be able to perform experiments. Basically, it exposes the switching infrastructure of the network to programmer control as part of a distributed system. And so one model would be the end-to-end model, where the distributed system is all overlaid on the internal networking infrastructure. But another perspective is one where, in fact, the network can be a participant in the distributed system and morphable to the programmer's needs. And this is certainly in the time frame that we started the project in the early and mid-90s, a very unorthodox perspective. It's interesting, I was looking at the initial SwitchWare proposal, and we actually wrote it in the late fall of 1996 based on ideas that we had been working on at Penn. So it's sort of like a decade from when we wrote the proposal to DARPA. So virtual infrastructures, if you want to think about changing the network, you have to decide where are you going to change the network. So one way to change the network would be to work with overlays, but you don't get complete control of the underlays. You don't get to change them. The question is, where do you build the interoperability layer for the infrastructure? So IP is a virtual infrastructure. The real infrastructure, the hardware, is living down here, the trunk lines, etc. The question is, when you're building applications, what is it that you write on top of? Well, when you write an IP application, you're assuming that there's an IP infrastructure there, and that infrastructure is virtual. It's overlaid on top of a bunch of other technologies, and it gives you a uniform view of what's going on under there. So if you're looking at building a virtual network infrastructure, you want to focus on the waist of this hourglass and focus your attention in introducing programmability at the waist of the hourglass. And the question is how to do that. It's obviously non-trivial, and I'm not convinced we completely succeeded, but I'll try to take you through some evidence that we made some progress with a programming language-based approach. So this was what we tried to do. We tried to make the waist of that hourglass, the interoperability layer, programmable. So the high-level goals, sort of the bumper stickers for this, we wanted to create programmable network nodes and standardize the programming model, not the nodes. So you might have a bunch of technologies living underneath the waist. That's okay. But what you'd like to do is standardize the programming model so that when programmers wanted to build distributed systems and to create novel distributed systems, they had a standard programming model for the nodes with which to do this. We wanted to move, basically we had the bias of programmers, which is we'd like to change from the political tempo of something like the IETF. We come out of the networking community, so the IETF is the standards body that contemplates and mulls over decisions and eventually says this is a standard, to a technical tempo where your ideas get out in the form of code. And the web was already evident then, and we were watching what was happening at the edge, where people were being creative and introducing new content and new ideas very, very rapidly. And so that kind of excitement was something that we felt might be something that we could get at in the networking world, where there seemed to be a lot of networking ideas, but very few of them were making their way into the infrastructure. And the example that we looked at was multicast, where for 10 years people tried to hammer it in to the core infrastructure and had very little success. And a lot of that is because there were many constraints, some of them economic, some of them technical, but most of the technical problems got solved, and the constraints were deployment, standardization, etc. So we felt that we would at least take a stab at trying to make this shift, moving from the political tempo dictated by standards bodies to what we felt was a technical tempo that was dictated by people's creativity and ability to generate working code. We had to balance a bunch of features. We decided that the trade-off space that we wanted to manage was between usability, flexibility. We wanted something that was a Turing machine, basically very complete. We had to figure out how to restrict it to provide security, and without too much hackiness, try to provide reasonable performance. So we made some internal decisions that we debated. The decisions at Penn were made amongst Carl Gunter, Scott Nettles, Dave Farber, and I, and we decided that we were going to try modern programming language technology. We did a few experiments based on threads, showed us we could context switch much faster. We believed that in the core of a network node you were going to get a lot of multiplexing, and we felt that this context switch performance was very attractive. We felt that the programming language technology was such that we could provide verification, and there seemed to be some possibility using type theorems in languages like ML for providing much stronger security. So one of the things that we set out to do, at least, was to try to produce a couple of type theorems that would be able to address limitations that would, in our minds, provide some more security for the system. So the question was whether we could use these high-level languages to try to provide a switching infrastructure. And that was the high-level goal. Yes, sir?
What's happened in the last sort of 5 years in terms of programmability of network infrastructure? I mean, so SwitchWare sort of has as its assumption that, that there's a API that these routers and various network nodes can be programmed. Have things actually progressed towards the nodes being more intelligent, or are they just as dumb as they?
Well, that's a great question. I mean, the progress has mainly been towards intelligence. The question is, how is the intelligence used, and what problems does it address, and who can use it? Okay, so what you see is that hardware performance has been used for deep content inspection. And so that means that you look deeper into the packets and spend a lot more energy on finding out what's going on in there. There's a lot of complexity in the code. So for example, if you look at the router code, I've read estimates that iOS is somewhere within the same order of magnitude as the 5ESS code from the telephone system, so that their operating system for routers has reached a level of complexity that is roughly that of a traditional telephone switch. And so there's a lot of programming there, but I would challenge you, other than in using a web server, to get access to that capability for your own use. That's what's very hard to do. So as an overlay, you can get access to the network, but you have very little ability to program it. So does that answer your question or not? Does that help?
So to summarize, there's a whole bunch of code running on those switches, but no one outside of the switch manufacturer has access to them.
That's one way to say it. Sure. I mean,
They don't have an incentive to open the thing up as a platform.
That's how they achieve safety and security.
they don't have it.
I mean, within an enterprise, I mean, what's going on? Like, I'm totally naive about this. So like when we buy routers, I mean, does an enterprise do more stuff with them? You know, I mean, other than the usual stuff, like would we, like if we wanted to do experiments, like would we have any hope?
Well, here's what you might have access to. So you could view lots of boxes as comprising your network elements. So one place where you might have some programmability is if you use, say, an enterprise firewall. So you'd use a programming language, which would be a packet filtering language. So, you know, it all depends on your perspective of what the network box is. And so in that case, you know, you'll use a language that's essentially a pattern matching language, and it may be a pattern action type of language, but it's not typically a very, very sophisticated programming language. Okay, so we initially, and this model is due to Carl Gunter, broke the language solution up into three parts. We focused on a switchlet language with the intention of allowing users to get access to the system. And what we wanted to do was provide either a restricted CAML. We weren't sure whether we wanted to provide a restricted CAML or a domain-specific language that would be offered to users. We knew it had to be restricted because we had shared network infrastructure. The question is, how much flexibility, usability could we get while providing enough restriction to make it safe to let users reprogram the roles of the network elements? There was a wire language, and this was for communicating. And so you could think of this as being something like a Java or Camel bytecode type of thing that would be used for moving data between the network elements. And then there'd be an infrastructure language, which is the language that the switch was actually programmed in. And we were enthusiastic enough, true believers in the language technology, that we believed we were going to run an enhanced version of ML on the bare metal, basically the programming language runtime on the processor with no intervening operating system. There was some very good evidence from MIT that you could do this, and so we were pretty enthused at the time about trying to do that. So these are kind of the ways in which we separated concerns in the system design. Alex?
Is the wire language a serialization format, or is it an actual language?
We felt that was where the rubber met the road as far as interoperability between nodes was concerned. And so I could think of that as a serialization language. That's an easy way to think of it. But what it does is it allows, for example, when you try to build a distributed system, rather than for this thing to be an island, okay, what we were worried about was building networks. So you'd have to have collaborating sets of nodes, and you can think of all the kinds of collaborations that have to go on in a network node, for example, to preserve routing and have other distributed algorithms running. So I'll show you some examples when I talk about the plan-based firewall of how we use the wire language to provide some enforcement. Okay, so this is the basic SwitchWare architecture, and this will give you the outline of what I'm going to talk about. So there were a variety of systems built. This was a big systems project. Multiple doctoral students were involved, and industry at Belcor, which is now called Telcordia. So we had expertise from the networking industry, and we had programming language, operating system, and networking folk all working on the project. Alex worked on a predecessor project called Protocol Boosters, so he's familiar with some of the agenda. So what I'm going to do is I'm going to talk about the alien node, which was really the most direct attack on how to build a node. Then I'm going to talk about PLAN, the packet language for active networks, which was another way to do switchlets that used the domain-specific language rather than a restricted ML. And then I'll spend only a couple of slides on the low-level stuff, which guarantees the integrity that is being assumed by the upper-level stuff. Okay, so the Alien was an active loader, and what you mean by an active loader is the following. You have to have some way for code to come in the system, you have to have some way of restricting what the code can do and add new services, and you have some base layer that loads the code in. And we had a combination of a CAML runtime, and we were using Linux as the operating system just because it was convenient for us to build on, and there were a lot of tools available. In particular, we liked OCaml as an environment, and I understand that there's at least some interest in OCaml inside MS. I'll explain what the protection boundary and mutability boundary are as I go through the talk. So what the loader does is it has some startup routines. It can do program loading, provide a system console. This is designed to be as thin as possible. This is something that has to be everywhere so that you can load in additional code. The loader's immutable. What is mutable, meaning you could change it. Change the functionality is the core switchlet. So the core switchlet is this is the mutability boundary. So the loader is immutable. The core switchlet is privileged and mutable. Okay, so that's how we broke things up. So this doesn't change very often at all. You could look at this as being sort of like a microkernel type of thing that doesn't change very often. And you load in all the new functionality in the core switchlet. So if you really want to update things, update services and code, if you need privileged functionality, say for example direct device access, this is where you do it. You do it in the core switchlet. And the advantage is that if you do it here, then you can decide whether or not to offer it to things coming in from outside. So the examples are things like thread access, message logging, and what we've added here is some policy. The libraries have everything else. So they have IP and UDP. Basically, it's like a user space IP, user space UDP, any sort of utility functions you need. This doesn't need any privilege. It's a library. This needs privilege because it's getting access to OS features and device features that don't share well in an arbitrary way. So what an active packet looks like is this. There's a link layer header. There's an active network encapsulation protocol header, and then a secure active network environment authentication. Basically, it's a hash. And what it does is it proves that the code came from somebody. And what you would typically do is send some code to a node that was going to run the code. It would look at it. It would sign it and say, give me this ticket when you come in again. And then it would allow access to that namespace. Otherwise, you didn't have access to the namespace. So what you did is you gave views of the namespace to arriving code based on whether or not they had the credentials presented to be able to have access to the namespace. And so this was a very programming language view of how to restrict access, but since we had multiple nodes involved, it was easiest for us to try to use cryptography as a means to validate that in fact the required authentication had occurred. So cryptography was used as the basis for showing that certain checks had been accomplished in the system. And so this is a pretty standard layout. The func is called with code data and the function name as arguments. Basically, if you don't have access to something in the namespace, you can't operate. And so the namespace is kind of the keys to the kingdom here. How well did it perform? Well, by today's standards, probably not very well. You're talking about, say, 10 millisecond pings here for local area network connectivity. There's no big distance being traversed here. 500 megahertz machine. Ethernet was fast enough. It wasn't like the packets were getting choked. this was due to the namespace building up over time. What this is just a number of trials. So you'd basically do 1,000 pings, and what you found is at ping 1,000, some of them were getting slower, and the reasons were garbage collector-like reasons. Alex?
Sorry, what are we measuring here?
You're just measuring latency. So what you're doing,
running your code.
you send a packet to another machine and it comes back. Okay, so it's a ping, but it's done with an active packet of the style of this. Okay, so what happens is it goes from one active network node to another active network node, and then a reply comes back. And so what we did is we traced the timing using the timers on Linux to see how long things took. And so what we wanted to see is, was this completely irrational? Relative to a standard ping, yes. Where was the performance penalty paid? It might surprise you, but a lot of it was in the authentication, the buffering. The CAML overhead was not very large at all. There were transmission-related costs, but with 100 megabit per second Ethernet, those are very low. We believe, that almost all of these costs are addressable with Moore's law changes. I mean, there's nothing fundamental here, and the relative overhead of using CAML is small. So I guess our feeling was, from having built a real system here, that using modern programming language technology doesn't cost you much. The thing that was more expensive than anything else was the crypto, but that'll cost you something if you do it with IPsec or anything else anyway. Yes?
Sort of a question on the previous slide and then one on this one. The model, though, would be is I send the code once, and then future packets that I send would normally just sort of reference that existing code, right? So I guess I don't quite understand why you were seeing it building up, or I imagine the first one's slow, and I expect the rest of them to be faster and at roughly the same speed. So, but just for this test, every packet was sort of installing its own new, ping reply code, or
the test is not really showing the initial load very well. Basically, what we were interested in: did we have memory leaks? Were there any extra costs in using a sophisticated language environment? And what we found was there was a small additional cost. And these additional costs over time are fixable. I mean, what we did is we talked with Xavier Leroy about a particular algorithm that had been used because we were adding elements to the namespace with each ping, and it was a solvable problem. But one of the good rules of thumb that I think we all use in the systems community is truth in advertising. And we said this is something that you never would expect, because nobody would ever expect you to be loading and loading and loading and loading in the environment. That's not something that you would normally see. So when you do performance debugging, this wouldn't be the kind of thing you'd see. So this is what you get from trying to do something different with a programming environment that wasn't optimized for guys trying to do networking with a sophisticated software development environment. So we reported it. Yes.
I'm a bit confused. Maybe I'm lost.
Oh, that's okay. Well, I'll try to unloose you.
So this is, I understood your last comment about, this isn't something you would do. So each one of these is a new type of protocol, in essence, or?
It's not a new type of protocol. What it is you're generating one of these packets, okay? And in the packet, what you have is code that says, send me back, and here's where I came from. Okay, so a normal ping is enabled with hard-coded logic in the IP stack. And so the difference here is that what we're doing this with is a completely programmable node, and it's a program that says, reflect me back to where I came to where I came from, and so it's a very simple application, but it demonstrates moving through the network. It demonstrates network functionality, and you could do it, in as long a network as you wanted. So.
Then that this is the expected behavior for any active protocol. I mean, it's the simplest possible example of an active protocol.
It's pretty minimal. I wouldn't go I wouldn't go on television saying that it's the simplest possible, but it's about as simple as you can get. It shows motion through the network, and it doesn't really do much work. That's why most people, except when they're aggressively firewalling, allow pings to go through, because it's a functionality test but nothing more. It says, is it reachable?
Flip over to your. So I guess the thing that I do find worrying here is that you've got 3 modes in that graph, as I see it, and they're all tending upward.
Yes.
So how?
Well, they were features of or bugs relative to this application in the programming language environment, because it was unexpected that we were going to do things like send a request to load a new program every every 10 milliseconds or so. And so what happened was the programming language environment did not expect people to be load, and that's really what this looked like from a workload perspective. And so what happened was you started seeing these kind of funny phenomenology. And so when we investigated where the costs of that were with very careful traces, it was basically that the namespace, which was being modified, was being updated, and there were essentially 1,000 names for ping.
So this is 1,000 protocols. So then, for example, if I just had my new replacement for TCP, it would just be a single protocol, and even though I used it for lots of different things, presumably, all the instances would have the same signature. They would match into the same place in the namespace. So I would be on the far left-hand side of this.
Yeah, you're not paying.
But not the far top right.
Yeah, you're not paying all these funny penalties. But they did happen, and since we were interested in the programming language environment as an infrastructure for this sort of thing, it was kind of a very interesting corner case for programming in CAML.
Far right-hand side, I should think of as I've got 1,000 new protocols active protocols I've introduced.
That's the easiest way to think of it.
Okay.
And it's a stressing sort of thing for the environment, and in a big switch based on the version of CAML that's here, maybe that wouldn't be outrageous, but we found it kind of interesting, but well within the range of feasibility. I want to move on a little bit beyond Alien, so I guess I've got another 25 minutes according to the clock. So keep after me with questions, but I'll go a little bit more quickly because I want to get to the where to go next part of the talk. So so basically the story here is that almost all of these costs are addressable with Moore's law, number one, and the only part that Moore's law can't really solve is the transmission-related stuff, because it's not going to be able to deal with wide area network latencies. It can't make the speed of light go faster with Moore's law. And the CAML overhead wasn't bad. Alex?
So the kernel wire, is that the transition from the wire into the kernel to user mode?
It's basically kernel to user mode buffer movement and stuff like that. So that's a memory issue. You could argue that the memory problems will stay there because DRAM doesn't get fast.
Well, I guess I was actually going to argue the other way, that if you actually want to install this on a network element like a router or switch, maybe you get rid of some of those transition costs.
Because it copies with a crossbar or some other element that's highly parallel. Maybe so. I mean, it'd be an interesting thing to experiment with, but we didn't do the experiment. So let's look a little bit at plan. This was work that was led by Scott Nettles and Carl Gunter. And the basic idea was this was a pure active packet-based approach. The active packet approach is one which is focused on blobs of code which carry the functionality around in the network. And so the question was, if you wanted to build a pure active packet approach, how do you build a domain-specific language just for users to use in controlling the network? And one of the real insights of the group that worked on Plan was that if you took a domain-specific language, like a glue language like the Unix shell, and used Alien's privilege mechanism to extend it, what you could do is you could basically defer any sort of privileged operations to the router in the same way that privilege in Unix is associated with programs. It's not associated with the shell. The shell has no notion of access rights or privileges. All of that stuff is pushed out to the file system. And so the idea, the insight that these folks had in thinking about their packet language was the idea that they could push much of the issue of privilege to Alien. And so active extensions were used for privileged things, a la that model I showed you of the core switchlet being the place where the privilege boundary happened. And then the glue language could be used for constructing network programs. So Plan, the language is designed to be safe and simple. Everything is in the packet. Services, however, say for example in an Alien architecture, may or may not be privileged. So for example, installing new code may require privilege, right? To install code on a specific router, you may require privilege. So the question is how to do that. So services are general because they're potentially usable by anyone depending upon your model of services, and they're provided on the active network node. So let's look at managing this. You may want to allow Joe to do a service install. So Joe works for Verizon or AT&T or UUNet or whomever your favorite ISP is. So it may be okay for Joe to install a new service. But Ed, you may not want to allow to install a new service. So you say, okay, Ed's not allowed to do this. How do you make those decisions? So if you take a look at a plan packet, you might allow the default user to perform routing. Okay, that's kind of a simple service that you give today on a router. And you may want to allow them to send packets. Again, you're going to need to be able to do that if the element is a piece of network infrastructure. Joe, however, may be a privileged user, and in addition to routing and sending packets, you may want to allow him to install new code. Or he may pay. You know, what one model is that Joe pays to be able to install packets. There's many models, but you have some desire to separate between what Ed can do and what Joe can do. So the default user can send packets, but can't really change the way they're sending packets. They can't change their usage parameters. So if we use the economic model, we may want to allow Joe to be able to send lots and lots of packets because he pays more. That's possible. I mean, you can think that that one way to start getting more bandwidth is to allow the bandwidth to be available to power users. And this would be allowed and easily doable. If you disagree with that philosophy, you never allow anyone to do this. But the point is that now you have the ability, using privilege, to control something like sending packets in this way. So what's the security procedure? Well, you arrive as the default user, so you might want to install something. Figure out that you're Joe. Do the install with a namespace adjustment. And then once you've determined that it's Joe, then you allow more bandwidth. Okay, so here's how you can have a per user usage adjustment in network capability. The basic unit, this was something that Michael Hicks designed. He's now on the faculty of the University of Maryland. He designed this unit called a chunk. It's the unit of evaluation. It can be manipulated as data within the planned program. So in the same way that people have perversely rewritten Unix shell scripts using Unix shells, this allows the code to be manipulated. Turns out that you can do quite a lot with this. It's what a chunk looks like. It has fixed fields in the chunk. The chunk portions of the code can be manipulated. The ping packet looks like this. There's a destination. When you get to the end, you print an acknowledgement. Arguments are the source and destination, and the function you call is ping. Here's where you use the digital signatures and authentication. If the signature is appropriate, then you perform the namespace adjustment and perform the evaluation on the chunk. So here's where the cryptography is meeting the programming language in this model. So let's look at an application that we found interesting because it changes the perspective of how you do things. So rather than filter external packets, so dropping them or allowing them in, you restrict their privilege. So what you would do is you encapsulate an incoming packet with a service restricting, basically an encapsulating type of chunk. So here's the setup. There's a trusted network, the source, firewall, destination. On an untrusted network, the guy on the trusted network is going to try to send a hey, are you there packet, a ping to the untrusted network. What the outgoing ping looks like is a chunk. It hops through the firewall to the destination. When it comes back, now here's the issue, right? The firewall is supposed to be protecting the trusted network. How does it do that? Well, what it does is it wraps it in a restricting in a restricting chunk so that it can't do anything evil when it gets into the trusted network area. So this is kind of an example of how you can use the fact that you've got programmability and programmable packets to change the way you build a distributed system. I mean, that's a point that I want to make, is this is a way to build distributed systems.
Question?
Yes?
What if both were actually trusted? Would it just pass the packet through? I mean...
Sure, you could do that. I mean, this is just meant to be a worked example of how you would use this notion of a chunk to restrict access to something that came in from the outside. Okay, so that's what we did here. We wrap it up and it's the acknowledgement, but we restrict what it can do. And so what we've done is we've transformed the problem in some sense to one where rather than just not let the acknowledgement in, what we can do is we can let it in, but we don't trust it any further than we should trust it. We trust it to say, yeah, I'm there, but it can't do anything else.
And are the policies installed because some out-of-band mechanism to say who can do what?
The policy's made up by the programmer, the person who's the person who's installed the code in the firewall that's doing the wrapping.
Right, but I guess the question is, if I want Joe to be able to install code, how do I specify that? And how does Joe get the necessary cert or auth data?
You'd send code to the node with appropriate authentication that would allow him to install the code that would do the wrapping. So you definitely have to have. There's a hidden overhead here of a PKI in the way we've done things, but once that's in place and there's programmability in place, this provides a model for performing the programming and operating the system in a distributed way. Is that answering your question or not?
We can talk about it.
Okay, that's fine. Here's how the firewall would wrap the code. There's a wrap function that says no resources, and then there's a signature that basically says this is from the firewall, and so you know you don't give him any resources, but he's just saying hello, and that's it. So you get back your it's alive and nothing more. Let's see, performance a little better than the ping. These were faster machines. The measurements were done later. Not a huge. Most of the penalty is in the examination. Size doesn't really make a huge difference. Adding the firewall function doesn't add a huge amount of performance overhead. A lot of the penalty is again cryptography. It's expensive to do. Let's look at the last part of the picture, which is how do you ensure that the programming language is able to provide the checks and do the restrictions that you want it to do? That's kind of a key question, because the operating system community will argue, well, wait a minute, you can't protect about some guy who is violating your protection model. He can get in your address space and then it's all over for you. So the question is, if you were going to build a node where the programming language runtime was providing the protection and enforcement, how could you do that in a robust manner? How could you ensure that what you had built, the type theorems that you were using, etc., could be enforced? So that's an integrity question. And so that's the last piece of the puzzle for us. Bill Arbaugh, who's also, like Michael Hicks, a professor at the University of Maryland, focused on building a secure bootstrap. What a secure bootstrap is it's a boot for the machine that guarantees that the machine that you proved that the runtime worked on and provided the integrity checks that you wanted, the dynamic integrity checks that are provided in the language, are actually what are being performed. So what AEGIS does is there's a read-only memory, and what it does is it checks and sees that the signature of the next level in the bootstrap has been verified, make sure that it hasn't been touched, and then and only then, if it satisfies a cryptographic check, will it actually execute that code at the next level. So the basic idea is you go through the steps of whatever infrastructure you have, you check the signature before you pass control to it, and when you get to the top, you know that everything's integrity has been checked. Because what you've done, you're not doing dynamic checking of the node, and you'd like to have dynamic integrity checks. And so for example, somebody doesn't get underneath the operating system if you have an operating system bug. But this is a model for making sure that at least the operating system that you shipped is what boots. And what's shown in the green box is that if it doesn't pass the integrity checks, you reach out to a trusted repository and get correct code. And then another piece of the picture is resource control. And the question is whether or not you're going to do the resource control in the environment. There was a thesis that was done by Paul Minaj at Cambridge, which I worked with the University of Cambridge on. And what it did was it built virtual machines that split the operating system, execution environment, and application using an operating system called Nemesis that was built at Cambridge, and some modifications to the runtime systems that guaranteed, for example, that somebody just didn't spend all of the programming language environment's resources on garbage collection, basically a garbage collection-based denial of service attack. So some subtle but very intelligent changes to ensure that you could multiplex and share the system. So that's the SwitchWare architecture. I took you through its pieces. I think from a systems perspective, it was a very interesting project. It taught us a lot, and we were pretty happy with the output. The code is still available for Plan, Snap, and a lot of the alien code is embedded in the Plan environment, and these are all available on the web, although I haven't checked recently to see if there's been any logical bit rot on the code. The point of the talk is supposed to be lessons learned, because I've been very interested. I mean, really the spur for me coming out here was missing a talk that Jim gave at the University of Pennsylvania on singularity. And I looked at singularity and I said, man, these guys are thinking in the right way, and I want to talk with that group. So I'll take you through what I think are some core lessons that we learned, like stepping back from it as a systems effort. And I'm glad to talk with anyone after the talk as well. We didn't remove interoperability problems. We moved them around. Okay, so there is still interoperability problems. You need the same programming model everywhere. So I think the kind of key thing is we did show a way where you could get programmability everywhere, and you could accelerate the network evolution in that fashion, because we did show how you could build a variety of programmable enhancements. I didn't talk about it here, but there are a variety of technical papers that show how you can build elements like an active bridge, where you can load code on the fly to build a bridging element, and other things. The performance, even on conventional PCs, was completely acceptable for access networks. The active bridge in 1997, almost a decade ago, was doing about 53 megabits per second. So I challenge you to get 53 megabit per second service at home. So for access networks, this is still fine. OCaml was a big technical win. I mean, I stand strongly behind the choice of OCaml. The people who worked on the project are steadfast in their support of using the language. They say that learning it was one of the best things they've ever done, and they use it in projects. They use it in projects now. It was a marketing lose. It was a marketing lose because the community was too small for a lot of take-up. And one of the things that we didn't spend a lot of effort on, and I understand that you're using C# for singularity, so I don't think you'll face this problem. But there was a very small OCaml user community in the 1997 time frame, and some of the other active networking projects that were around at the time were looking at using Java, and there was much more take-up because there were Java programmers. So we didn't really look at the population of programmers. We tried to look at it in a scholarly way and say what were the features we wanted, and we drove everything with the language choice. And I think in retrospect, I would have been happier with some fashion where we got more take-up, and maybe I could have thought of another way to do that, but I think it would have been more satisfying if there was more take-up of the technology, because it really did seem like a very interesting way to go. Restricted languages for packets, definitely a win. We showed how you could build new services into the network. A small internetwork was built, interconnecting Ethernets and IP-based networks by Scott Nettles, Michael Hicks, Pankaj Kakkar, who I think is at Microsoft, and Jonathan Moore and Carl Gunter. Very interesting project. I think it's kind of interesting to look at exactly how to make the cryptography dance with the programming language. And I think that that's still an interesting problem, and I intend to have a little bit of a discussion with the Singularity team after my talk to see how it's been addressed. I felt that it would be better to maybe get this stuff up here and then see how it's been addressed. We didn't really allow enough time for the network work versus the node work because we chose to do two things. We chose to solve two problems, and it would have been better to have enough time to sort of solve them carefully in sequence, which is pick a language environment and build a programming environment, and then flesh it out into a network. But what we tried to do was both at once, and I think that we did not have enough time to really flesh out the network and refine the programming environment. So one of the kind of key things you get by building a network and deploying it is feedback from users and experimenters that you can use in refining your environment, and we never really got that. We built it, we gave it out, we had a lot of downloads, like 500-600 downloads for plan. There were some users because people did experiment with it, but again, it wasn't a big enough community to really create a huge snowball and get us as developers a huge amount of feedback that we could use in refining it as a network infrastructure. And I will say that convincing active applications is hard because you have to solve the network problem before people get interested in writing applications. That is, people outside of your group. And if you're focused on designing the environment, what do you focus on? Do you focus on the applications and keep the environment static? Or do you sort of have two balls in the air at once? It's a kind of an interesting management problem. With a large enough group, you might have divided things up into a network group, a programming environment group, and an applications group, but we didn't have that scale, and so we found that to be a bit of a challenge. But it's absolutely important to have compelling applications because that's what brings in the user community.
Was the problem that you didn't have enough people to build the active applications, or figuring out what the application should be in the first place was hard?
I don't think we had any trouble thinking about what the applications could be. But for the applications to be compelling, they had to be more than kind of hero programmer exercises. So you could think of something where, what I imagine in the future is that I am the god of networks. And I want to reach out to 1 million cameras, and so I can get how you hear your name in a room and it catches your attention. I'd like to be able to see if something of interest to me pops up on a camera somewhere in Zurich, and flow that to my desktop and say, hey, JMS, here's something that concerns you that's going on right now. Without putting some functionality in the network, that doesn't appear feasible to me with scale. Having some little sort of watcher in the network, some sort of JMS friend that says, hey, that's an interesting vid, maybe I'll forward it to JMS. That's something that I could think about doing. So self-paying information transport, the world's most awful acronym, SPIT. But SPIT is the idea that what you could have is packets with basically little kitties of cache that move through the network, and the active network node could take off the charge for transport and basically start allowing you to have economic algorithms in the network. These are things that don't really get interesting unless you have scale. And so that's why this ordering of events, which is let's build the environment, let's do some experiments, let's build a network, and then let's get some users who are building applications is the right. We thought of plenty of applications, but we just didn't have the network to do experiments on to make them compelling. So I don't think it was lack of ideas. I think it was just lack of a big enough community. That's my belief as opposed to any sort of experimentally validated truth. Yes?
And while you were going through a lot of this, the application I was sort of thinking about was Skype. Right, and I'm kind of wondering if, Skype from a security point of view must be a nightmare. And the general problem is, how do I set up a peer-to-peer connection across all kinds of firewalls, yada, yada, yada. And I think usually what you do is you get someone on the inside to agree to sort of punch a hole in the security model, all right? And enough people agree to do that, and you can now do your application. They're not actually trying to solve the security model. If you were to add, a real sensible security model to Skype, I'm not sure it would actually change the sales that they're, and so I'm kind of, I mean, if you wanted to do something like this, like a Skype application on top of your thing, how would you ever get the snowball going so you could actually compete with Skype?
Well, that's a great question. I would not want to compete with Skype as it is today because it's got a user community, but it would be interesting. It would be interesting to try to take on just as a kind of a test case. I think what I would try to do is I would probably try to think about how to identify the characteristics of a Skype stream that I would want to have at my enterprise boundary so that people wouldn't feel the need to punch through security. If you provide an acceptable service model with your network infrastructure, people don't feel compelled to talk somebody into punching a hole through it. They just accept it as being what it is. So for example, if you let I don't know whether you do here or not, but we let SSH through, but generally don't have sort of raw telnet and FTP and sort of all these other services. We've made policy decisions. And so the kind of questions that Alex was asking about the active firewall would be the kinds of things you try to address in a Skype sort of scenario. It'd be fun to build. Maybe I'll ask some master's student to take it on as a project. It'd be kind of fun. I mean, I'd be interested. Maybe it'd be interesting to try to do with your stuff. So I'd have to work through the details, but I think it's definitely doable. I think it's got some advantages. Is that you could restrict what the flows are. You could restrict what Skype has any kind of view of, because they have to have some code on the end hosts, and so that means they have to have code inside. And personally, I don't know what it's doing.
Security violation would be, say, Google Toolbar.
Yeah.
Okay.
Yeah.
What could you offer some way that an enterprise could download the Google Toolbar and feel safe? Okay. Well, but
I
Skype
think you could. It's not clear that that's a network. It's not clear. That's a great question. It's not clear that it's a networking question in a pure sense. What you'd have to have there is you'd have to have a very distributed systems perspective, where there was cooperation between the network element. Say, for example, the device says, "Here's Google Toolbar stuff," okay, and you identify it. Okay, you recognize it. And then on the way in, you decide what you're going to allow that thing to do. So you essentially have to create a virtual environment that extends all the way to the host. And I think if you did that, you'd probably be okay. I mean, one of the challenges that we've had with the web is that you inherit the privilege of the browser in the end host. And so what happens is, when somebody downloads code from the net, all of the privilege inheritance occurs that allows something like the toolbar or any other active content to have the full privilege of the user, unless somebody tries to do one of these tricks of cherooting something and try to isolate it. And most people are too, that's a clumsy solution. And so I think you could do it. I can't say based on any experiment that we did that that yes, we have a definitive experiment to do that. There was work I did with one of my doctoral students, Sotiris Ioannidis and Steve Bellavin, on something called a sub-OS, where we looked at building about like 1,000 or so subdomains that were supported by a little bit of extra state in the kernel that let stuff come in with low default privilege. So for example, you could have the toolbar come in and give it a very low level of privilege relative to your standard rights as a user, and gradually maybe open up things if you wanted to, or not ever open up things. So the idea is that you change the granularity so you get much more fine-grained privilege resources you allow access to. So that was the idea in the sub-OS, basically to provide finer-grained access to resources. And that might be something that when combined with these approaches would be valuable. But I mean, it's interesting. I mean, these are the kind of problems that plague us all every day. I mean, you know, do you download the content and get the service? What are you really buying? You know, it's...
But the security guys don't have the political juice to stop people from downloading things like that. Then those guys, the marketing guys, get to choose what the security model is.
Sure, and I mean, you know, the issue is that they don't necessarily have the tools to help you, even if you were willing to be helped. I mean, I think that's that's the bigger problem, is that you know, I think most of the security folks are generally trying to do the right thing, but they have a blunderbuss. It's not really fine-grained enough to do what you'd really like to do. And you know, you may want to execute this stuff. You don't have an easy way to do it. But does that help? Okay, let's see. So, I mean, I'm thinking about some things you could potentially do with this model. I think that network elements have largely become switched, which means that they don't look like PCs anymore. They look like multiprocessors with huge interconnects. And that's to be able to support high aggregate data flows. And this was along the lines of the question Alex was answering earlier. So I think that maybe one model you could think of in the future is active network nodes that are distributed systems, where you have a very high-speed LAN or switch infrastructure, where the IP elements, rather than be routers, which are routers plus forwarders, you split off the sort of routing and policy decisions from the forwarding, utilize the highly parallel switching infrastructure, and control some of the policy, route flows, and any exceptional code events with an active element that sits on the LAN. So what you're doing is you're separating concerns here. Another model, this is something I'm working on now, and this is one of the things that got me juiced up about talking with MSR about singularity, is I've been thinking about the wireless edge a lot. And so a couple of years ago, I had some students build an internet mobile phone. Thing is big. I try to. It's not a StarTAC. I'll tell you that. It's good sized. You can tell from the WaveLAN card. Okay. So that's the you know, the ruler is the WaveLAN card. But these guys built a phone from scratch. Built it on a microprocessor platform. Used Blowfish to secure all the traffic. They worked. They wandered around the university campus. And so what I've been thinking about is how you build a mobile infrastructure where people can add services that they need as they move around in the system. So I've been thinking of using some SwitchWare-like thing over a virtualization support system, and some cognitive radio devices that are becoming available in the edge, to actually try to do some dynamic spectrum control and program the way my mobile devices behave at the edge. And so what I'd welcome is any discussion if you folks are interested in doing anything with code loading to deal with things at the mobile IP boundary. I'd definitely be interested in having that kind of chat. So SwitchWare was Penn and Telcordia. There's an extensive literature. You know, I tried not to give you an encyclopedia, but to try to take you through the stuff that was useful in thinking about the programming environment today. The resource-controlled active network element was a collaboration with Cambridge University. And I got machines and help at various times from HP, Intel, 3Com, and Nortel. And I guess I've probably gone 10 minutes over my time, but I'm glad to take questions now or later or lunch or anything else.
I have a question about,
Sure.
I guess, the programming model. It's the idea that I send you a packet with a bunch of code and data and I get a return, or does the return actually have to be part of what I send you?
The return has to be part of what's sent.
Okay.
And to me, that seems... The fundamental primitive should probably be moving a packet from a source to a destination. And so if you think about something like UDP, that's really how it works. And UDP is very primitive. It's essentially just a way to demultiplex IP packets at the edge. And TCP is more complex because it's trying to give you a virtual circuit model. So the return is scaffolded on the basic functionality, and you need a little bit of service. And you find that with ping too, that there's something that returns the ping that lives in the kernel. It knows how to do an echo reply if it's allowed.
So, maybe just a big comment perhaps. So you heard about Erlang, right? Used at Ericsson, which is a functional programming language that they've used for like more than 10 years. But I think that in using Erlang, it's mostly for call processing applications, higher level up, right? I don't know if they ever tried to use functional programming language as low as you have, in the sense of like more like at the routing level or switching, etc. Can you comment on that? Or?
Sure, we looked at Erlang very carefully, and what we were looking for, since Ericsson, we knew a lot of folks at Ericsson, and we talked with them a lot about Erlang, and they loved it. I mean, they were absolutely in love with their system. And so we talked with them a bit, and I mean, I actually was looking through, when I was preparing this talk, some of the historical background. And one of the problems was getting the Erlang environment in a way that we could do experiments on our platforms and things like that, because, you know, Ericsson is wonderful to collaborate with. My read on things was that it was going to require, at least in the form at the time, I guess it was like 95 or so when we were looking at infrastructure, that it seemed to prefer to run on their switches and things like that. And I think we wanted to be able to get experimental infrastructure to a lot of graduate students. And my read on things was that I wasn't going to be able to buy, even with the generosity of DARPA, to buy a bunch of Ericsson switches to experiment on. And it wasn't clear that, in spite of the language being really cool, whether we wanted to re-implement it, you know, implement in a micro Erlang. So we were well aware of their successes, and in fact, I will tell you, one of the things that convinced us that we could actually try this was that the Erlang folks were so intellectually enthusiastic about the use of functional languages in a major switching infrastructure. Maybe for different purposes, but you know, it really worked for networking. So yeah, we were very aware of it. We cited it in all of the early proposals, even saying this is something that is being used in industry and people are very positive about intellectually.
They were using it mostly for call processing applications.
Yes, that's correct. Yeah, because they were building big switches. The people had looked at this kind of thing. There were predecessors. So there was a system that was also built in Sweden called SoftNet that was built in the radio community. So what these guys did is they took, it was actually quite clever. They built a forth-based operating system, and they had packets moving around between mobiles, And there were very clever ideas. So they had a multiprocessing fourth implementation, and what they did was they had a communications processor which was essentially immutable, and then they had another processor which was mutable. I think they used 6502s, which were an old microprocessor, which some of you may be familiar with, but looking at you, probably not. It's yeah, a long time. So, but these guys built a reasonable infrastructure. They experimented quite a bit with it. It was a radio-oriented community, and what I did is I got all the literature from these guys. Half of it was in Swedish, which I can't read, but most of it was written in English because it was for radio conferences. That was written in English, and we read all this stuff before we got going because we wanted to start from the lessons that folks had learned. I became aware only after we had gotten quite a ways into this of work by David Wall, who had looked at a mobile code-like approach that kind of resembled the capsules work that Weatherall and Tenenhaus did. And so he had early work, and I think that was in Principles of Programming Languages, but it was in the 1980-82 time frame. Very clever stuff. And then I think that was about it. People had looked at mobile code approaches, and people had looked at sort of the node infrastructure, which SoftNet had been focused on for the mobiles, and I don't think they were thinking of a whole-scale revision of the network infrastructure, which is kind of the agenda that the active networks effort at DARPA had, and we took a PL-based approach because we felt that was a promising and underexplored approach. We thought, let's be a little riskier here and see what we can do. So that's what we did. We tried to make sure we knew what was out there, and didn't always succeed because sometimes stuff was done in obscure places. I think we should have probably caught the David Wall paper, but we didn't.
Well, let's thank our speaker.